Question 4. Compounds all have relative molecular mass of 58, and it wants us to work out, explain why determine the precise relative molecular mass of propanol and propene 2-ol by mass spectrometry cannot be used to distinguish between samples of these two compounds. Now, this is a very weird question, but the idea is it tells in the question they all have the same molecular formula. And they all have identical MR. So they have the same molecular formula, identical MR, and therefore it determining relative molecular mass would not be able to distinguish between these samples. They have the same molecular formula, identical MR. 4.2 uses spectrum to identify the compound. So anything less than 1500 centimeters to the power minus 1 fingerprint region. We don't really care about that for most questions, but some questions we might need to use a fingerprint region, or it might ask us questions about it. And then it says use spectrum to identify the compound. So we look at the peaks, and the peaks point downwards. So we've got a peak here, and we've also got a peak here. That's around 1600. This is around 3300. So if we look at the periodic table, and we go to table A, we know propene 2-ol is an alcohol, and the bond from 30 to this is OH, right? OH. 32, 30 to 35, 50 centimeters to the power minus 1. Just copy and paste it from table, and therefore the compound must be propene 2-ol. Prop dash 2 dash ene dash 1-ol. Because think about it, we've got propanol, it doesn't have an OH bond. Butane definitely doesn't have an OH bond. Propene 2-enol does, and we've clearly identified that there's a peak here which reflects the OH bond, so therefore the bond is OH because it's got a wave number at 32, 30 to 35, 50, and remember the peaks point downwards in the infrared spectrum. And 4.3 predict the relative boiling points of these three compounds from highest to lowest boiling points. Justify this order in terms of molecular forces. So we have propanol, propene 2-ol, butane. So this is obviously hydrogen bonds, oxygen and hydrogen. Hydrogen with an NOF, and this is oxygen. We've got butane, that's just van der Waals, and propanol, permanent dipole-dipole. So we've got prop dash 2 dash ene 1-ol, which is greater than propanol, and propanol is obviously greater than butane. 6 markers, so you have 3 stages, but for this, it's not really 3 stages. Well, it is, but we just need to talk about the intermolecular forces. I'm just going to summarize it really quickly. Prop dash 2 dash ene dash 1-ol has hydrogen bonds. Propanol has permanent dipole forces. Butane has van der Waals forces, and therefore in terms of molecular forces, the strength of intermolecular forces we've got hydrogen bonds, which are obviously greater. Hydrogen bonds are the strongest. Hydrogen bonds, we should also know van der Waals are the weakest, so hydrogen bonds. Then we've got dipole, which is second strongest, and then van der Waals, which is the weakest. And then you can know, once you've got this down, propanediol greater than propane, propanol is greater than butane, propanediol has hydrogen bonds, propanol has permanent dipole forces, butane has van der Waals forces. Just stating those simple things, then some molecular forces, and the strength of molecular forces of hydrogen bonds is greater than dipole, which is greater than van der Waals. And then you could explain van der Waals weak forces between molecules, hydrogen bonds strong forces between molecules, permanent dipole forces slightly stronger than van der Waals, and then you could talk about that. But that is the end of question 4.